Hi everyone, it's the Brainwave podcast where we discuss different papers about deep learning, machine learning, computational neuroscience, and other interesting topics. It's Ivan here and Pavel, and today's paper that we're going to discuss is GhostNet, More Features from Cheap Operations. It's a paper from Huawei and Peking University and the University of Sydney. Without further ado, I guess we're going to go into it. So essentially, the paper is about designing a new mobile architecture that is able to outperform Mobilenet v3, both in terms of accuracy and in terms of latency. So the paper proposes the Ghost module as sort of a drop-in replacement for the ordinary convolution, and the Ghost module has less operations and is more lightweight. And you can take almost any convolutional neural network and take the convolutions that you have in the architecture and replace it with the Ghost modules. That way, you can speed up any sort of custom architecture that you might have for your DNN. So the main intuition behind the Ghost module is the redundancy in feature maps generated by typical convolutional neural networks. So right here, we have a visualization of feature maps that are produced by this sort of input, a picture, an image of a cat, and you take some output of some layer in the ResNet 50 DNN model, and you can take different features, different output channels from a certain convolutional layer in ResNet 50. And you can visualize these different feature maps, and you can see that there's certainly pairs or triplets or several feature maps that are highly correlated, that are essentially describing the same kind of thing. So for instance, here 2 green ones, 2 red ones, 2 blue ones, and also there's another visualization of that in here, where you have also a set of feature maps, and you can see that there's groups of feature maps that are highly correlated. And this fact has been observed in the convolutional neural networks for a long time, and there have been proposed approaches that try to somehow reduce this correlation between different filters. But here, instead of trying to fight the presence of this correlation, the authors proposed to embrace it and just make the whole computation of this set of feature maps more lightweight, taking into account that there's groups of different feature maps that are highly similar. So in a nutshell, here's a visualization of how this Ghost module can replace the traditional convolutional layer. So in a traditional convolutional layer, you have a set of like an input tensor that has like a set of input channels, and you apply the convolutional operation. You have the output, and you have certain groups of channels that are highly correlated. Here, this is visualized by this sort of upper set of channels, and it's supposed to be highly correlated with the bottom set of channels. So what they propose with the Ghost module is to replace this single convolution with first a more lightweight convolution that is going to only generate these several feature maps. And then we're going to have a skip connection that's going to just put these feature maps to the output of the operation. And then you're going to have like some sort of lightweight operation that's going to take these feature maps and generate the similar feature maps that you have. So as this lightweight operation, they propose just to use a depthwise operation. Depthwise convolution is a lightweight convolutional operation where you have like a sort of a set of input channels, and you have a set of filters, and there's only a single filter for each of the input channels, and one input channel is mapped to a single input channel is mapped to a single output channel via a single kernel. So if you have 3 input channels, you would have 3 output channels, and you don't have sort of a linear combination. So in an ordinary convolution, you would have like for each output channel is going to be produced by a linear combination of different input channels. So here, one input channel is mapped to a single input channel is mapped to a single output channel. So this operation is more lightweight. It has just less computation because you don't have this kind of cross-dependency between different input channels. So what they propose is just to learn single kernels that would transform these input channels into some kind of correlated outputs. So you're going to have essentially the same output as you had with the original convolutional layer, but now these correlated feature maps are going to be produced with a more lightweight operation. That is a depthwise convolution. So
I wanted to ask, does depthwise convolution means that you have for computing it, you just take one channel, one input channel?
Yeah, so if you have, like, for instance, 5 input channels, a depthwise convolution would produce 5 output channels. And to produce every single one of those channels, it would take only a single channel from the input. So you're going to have like a single kernel for each. You're going to have 5 different kernels, and you're going to apply each single kernel to each single input channel, and then have 5 output channels. Each of them is going to be just determined by one input channel. So it's much more lightweight than an ordinary convolution. In an ordinary convolution, you would have, like, for each output channel is going to be produced by a mixture, a linear combination of those input channels. So it's going to have much more operations as a result.
Square of number of channels. If for each channel if we have 5 input channels, for example, and 5 convolution layers, we would have 25 times more parameters.
Yeah, exactly. So the number of input channels times the number of output channels. Whereas in the depthwise convolution, you have just one number of input channels. So it's much more lightweight. So what they're saying here is that there's a typical convolutional operation where you have an input x and you apply some certain function f and add the bias b, and then you have this output y, the output feature maps y. So they propose to generate some of the output feature maps by a lightweight function of some of the other feature maps. That is by a lightweight convolution, as described here. In one of their experiments, what they did was take a ResNet 50 model and replace all of the convolutions with ghost blocks, so that they got a ghost ResNet 50 architecture, and they compared it to a bunch of different filter pruning methods. So in filter pruning, what you do is you just try to remove some of the output channels from each of the convolutions. So you just reduce the amount of computations by just trying to prune some of the output filters. Here instead you sort of retain the same number of output channels for each convolution, but you use a more lightweight operation to compute some of those feature maps. So that results in typically higher accuracy for the ghost ResNet 50 model compared to, like, for instance, a bunch of different filter pruning methods. So here you can see that it performs better than all of those results on filter pruning on ImageNet, and it's actually not that far away from the original model they took. So here for the original model they have 75.3, and in case of S equal to 2, which means they have half of the channels, half of the output feature maps are generated by the ordinary convolution, and half of the feature maps are generated by a depthwise convolution applied to the output feature maps. So this S equals 2 results in like 50% pruning. So the number of flops is almost 2 times smaller, and you have almost the same top 1 accuracy. It's only 0.03% accuracy drop here. So if you prune more aggressively, you have S equals 4, so it's 4 times more lightweight. Then you have almost a percent drop of top 1 accuracy for the ResNet 50 model, and it outperforms a bunch of these filter pruning methods. So they took these Ghost modules and assembled an architecture that is that is based on a Mobilenet v3 architecture, but instead of having ordinary convolutions, they replaced it with like so-called ghost bottleneck modules. So they have a description of a ghost bottleneck. It essentially resembles a bottleneck module in Mobilenet, but it has these ghost modules instead of convolutions. So they have examples of like a stride 1 bottleneck, where you have like this is like this building block of a network, and you have a skip connection in the beginning. Then your input goes into a ghost module, then it has a batch norm, a ReLU, then another ghost module, a batch norm, and then it gets added to the input. So also here with the stride 2 bottleneck, you have a ghost module, then you have a depthwise convolution, then another ghost module, and it's getting added to the input. So they take these ghost bottleneck modules and arrange them in sort of the following architecture, where they have an input that is 224 by 224 resolution with the inputs, and then they sort of stack these ghost bottleneck modules and gradually reduce the resolution, and then in the end they have a 1-by-1 convolution, average pooling, 1-by-1 convolution, and a fully connected layer. So you can just have a look at this architecture and realize that it closely resembles that of Mobilenet v3. But actually what they found is that if they take this sort of architecture and compare it against Mobilenet v3, they can have a better accuracy versus flops curve for the GhostNet. So here are their main results, is that they took the Mobilenet v3 curve. So here's accuracy on ImageNet versus the number of flops, and then they plot the GhostNet results, and you can see that for a range of different size networks, they outperform Mobilenet v3 in terms of flops and also in terms of latency. So they have this accuracy versus latency graph in milliseconds. So they also outperform Mobilenet v3, some neural architecture search results as well. So this is kind of a very light backbone that you can use. And also you can, if you have like a certain custom architecture, you can replace ordinary convolution with these ghost modules and then fine-tune your model to get more lightweight backbone. So here, what we have here is just a comparison of GhostNets against Mobilenet v3 in a bunch of different models. So they have state-of-the-art accuracy here, and also they have tested this GhostNet architecture as a backbone for an object detection model. They took a one-stage object detector like RetinaNet and a two-stage detection model like Foster RCNN, and they took 3 different variants of backbones, that is Mobilenet v2, Mobilenet v3, and a GhostNet, and they found that in case of RetinaNet, they have almost the same accuracy as for Mobilenet v2 at almost 2 times less the flops, and for the faster RCNN model they have slightly almost the same accuracy as for the model with the Mobilenet v3 backbone, but also at a more lightweight. So do you have any questions, or we can go into details?
Does Ghost BubbleNet, Ghost BubbleNet mean that the convolution layer replaced by depthwise convolution?
Convolutional layers are replaced by these Ghost modules. So the ones displayed here. So you're going to take each convolution, and instead of a convolution, you're going to have this sort of subgraph where you have a single convolution, then a depthwise convolution, and a skip connection. Reference PyTorch implementation. So instead of a convolutional layer, you're going to have this kind of subgraph where you have a primary convolution. That is this one right here is going to be primary convolution. So you have your input x, then you feed that to the primary convolution. Then you're going to have a cheap operation, that is a depthwise convolution, and you're going to feed this result from the primary convolution to this cheap operation, and then you're going to just stack these two together via concatenation, and that's going to be your output. So essentially it's just this simple subgraph where, yeah, so you take every one of the convolutions in your network. No, you take convolutions in your network and you replace it with those subgraphs, and it's going to give you a more lightweight network. So they propose exactly that. Let's take these building blocks from a Mobilenet v3, and in place where you would have convolutions, let's put these Ghost modules in place. And then with these building blocks, you can assemble this classification architecture. So that's.
Thanks for your explanation. I have one more dumb question. Do they retrain the model from scratch, or just use the already trained weights?
Yeah, so that's a good question. On how do you, if you were to take a pre-trained architecture where you have convolutions and you have to replace these convolutional layers with these Ghost modules, how would you initialize that? I believe they just trained that from scratch, right? So they just changed up the architecture and then trained the whole network from scratch on ImageNet. They didn't do any smart initialization tricks that you can do if you have like pre-trained weights that you can transfer to these Ghost modules. I believe they just randomly initialized that and trained it from scratch on ImageNet, like you would like a new Mobilenet architecture if you were to produce one.
Okay, I see.
So this method essentially it's kind of an alternative to filter pruning. So here what you do is you replace your convolution with a convolution that has less output filters, output feature maps, but then you would have like sort of an additional operation that would restore some of these feature maps that were pruned. So it's kind of a potentially more accurate version of filter pruning. So that's kind of promising to me. In cases where filter pruning just results in a large accuracy drop, you can try putting these Ghost modules instead of just pruning your large convolutions. And I believe they did a sort of a ablation study where they tried for these depthwise convolutions, there's a question of which kernel size to choose, right? So you can have like a 3x3 kernel or 5x5 kernel, or it can depend on the original convolution. So their ablation study showed that you can just take a 3x3 kernel, and that's going to be optimal for regardless of the convolution kernel sizes in the original layer. So here for this primary convolution, you would have the same kernel size as the original layer. So, and this work was actually published at CVPR 2020, and there were some, I guess, people have built their object detectors and whatnot using this kind of backbone network, given that it's more accurate and more performant compared to Mobilenet v3. So it's kind of a great lightweight architecture to start from if you're looking for a fast and accurate kind of network.